Hello, everyone. My name is Robert Wille. I am with the Johannes Kepler University in Linz and with the Software Competence Center in Hagenberg, both in Austria. And first of all, I would like to thank the organizers of this workshop very much for having me here, giving this talk, but also for organizing this workshop in general, because I personally believe that constrained programming has a lot of potential for quantum computing, but they also, in order to utilize this potential, we also have to overcome a significant amount of obstacles and challenges. And both of that, the potential and the challenges, is something I want to discuss about in my talk, with a particular focus on using SAT solvers for quantum computing design. As you all know, SAT solvers have had a tremendous impact in the design of conventional circuits and systems. We're using SAT solvers there for a huge variety of design tasks, of applications. And I personally believe, and I still think, that this kind of potential is also something we can exploit in quantum computing design. And first solutions toward that already are available. And this is one part of the talk, of one aspect I want to cover today. And nevertheless, there are also a couple of issues and obstacles to overcome which prevent the use of SAT solvers in quantum computing so far, but where I believe maybe there are some ideas floating around which can help us overcome those challenges, even though it is not going to be easy. And those two aspects, how we can use SAT solvers today for quantum computing design, so what kind of potential we can exploit already now, but also what kind of challenges do we have to overcome in order to really let SAT solvers in quantum computing shine. Those are the two aspects I want to discuss in the next 40 minutes, approximately 40 minutes. And in order to do that, and in order to get that started, let me give you a quick introduction, a quick review on quantum computing in general. And I promise it's not going to be a huge tutorial. I just want to, set a little bit the context. So the first context is, of course, you all heard that quantum computing is really gaining momentum these days. So while quantum computing has been investigated for many, many years, if not say decades, it really took off in the recent years. Of course, with all the engagement by the companies shown here on the slides, we've got IBM, Google, Microsoft, Amazon, as old players, more or less old players, getting heavily involved in this technology, but also new startups such as Rigetti, IonQ, IQM, and so on and so forth. They are entering the field, and that's different to maybe the developments of the last century. Now we also got many applications with a long-term perspective, but also applications with a near-term perspective. And this makes quantum computing interesting today, that we have access to first quantum computers and we can use them for certain applications. And of course, some of these applications are applications where really using a quantum computer makes it different compared to using a conventional machine. Also, we see a similar process as in the conventional realm, and with respect to hardware, that quantum computers have become available. They are actually, some of them are actually available for quite a while, but the progress which are currently made is really impressive. And we have first publicly available quantum computers. And also, if you check out the roadmaps of those quantum hardware, for example, here the roadmap by IBM, you can really see a very impressive development, but actually in a development which is very similar to the development we have seen in the conventional realm, right? So first quantum computers, such as the one depicted here on the right-hand side, filled entire rooms. Well, this is the same what happened with first conventional computers, which also filled full rooms. And then, of course, you all know that we've got Moore's law, and we've got this tremendous development in the realization of conventional circuit and systems, Moore's law, exponential growth, literally the reasons why we literally have a digital revolution these days, or these years. And this kind of development has been observed in the realm of conventional computers, but we actually can see that also in quantum computers. Also right now, we are really experiencing that a very similar development in the realization of more and more powerful quantum computers are taking place. So in this regard, there are lots of similarities, but however, in order to utilize all this potential, of course, we need EDA tools. We need tools that are capable of managing this huge complexity. And here in the past, we've got many of those tools, and those tools indeed were able to handle enormous complexity. And constraint programming, or referring to the topic of this talk, SAT solvers are a main tool, a main feature we have here. So SAT solvers actually help to tackle many of the resulting design problems we've got from the ever-increasing complexity of circuits and systems. And then all those tools have been combined together into powerful design and compilation flows. And although, of course, we all relied on the physical accomplishment when it comes to conventional computers, without those software accomplishments, without the accomplishments from constraint programming, SAT solving, and so forth, we wouldn't be able to tackle many of these urgent design tools or urgent design tasks. And now going back to quantum computers again, well, we've seen the roadmaps, and similar developments for quantum computers can be seen as we have seen in the past century, in the past decades for conventional circuits. And now the question is, are the software tools keeping up with this development? And yes, there are several tools available. Most of you probably have heard about Qiskit. There are tools like Circuit, like Forest. So lots of really powerful tools are available. But I would say those tools don't utilize the power of EDA tools we take for granted in the conventional world yet. So there are some powerful tools, but not powerful in the sense that we have many tools which utilize constraint programming, which utilize SAT solving, and so on and so forth. And also when it comes to the entire design flow, of course, we have lots of questions. What will an eventual design flow, an eventual compilation flow look like? So I'm not saying there's nothing, but if we compare that to what we have available in the conventional realm, I guess we can all agree that there's a huge difference in the power of design tools and flows in the conventional realm compared to the quantum computing realm. And if we stay with that, then we may end up in a situation where quantum computers getting more and more powerful, while the corresponding software and design methods cannot keep up with this development. And so we may have very powerful quantum computers, but no efficient methods to use or to design them. And here SAT solvers obviously can be a major part in solving this problem, because as we have seen it in the conventional realm, SAT solvers have been used to tackle very complex design tasks. We now maybe can do that in the quantum realm as well. And this kind of motivates my talk here. I want to sketch two particular examples where I believe SAT solvers can help. One example where we already have successfully proven that SAT solvers can help, and another example where we have some ideas, but still some challenges, some obstacles to overcome. And those two problems, the first problem I want to talk about is using SAT solvers for what is called an exact quantum circuit mapping, which is part of compilation. And the second part is I want to talk about how we can maybe use, or how we can derive and SAT encoding for quantum circuits in general, so that we can solve general quantum circuit design tasks for that. So those two issues are going to be covered in the next couple of minutes. And again, of course, I want to start with the first topic, which is how can we use SAT solvers already today successfully, namely here in this example in context of a compilation problem or a quantum circuit mapping problem. So to motivate that problem, let's quickly check out how usually quantum circuits are designed and what's the typical flow. And to this, let us quickly review what is a quantum circuit. Well, a quantum circuit actually is nothing else but a cascade of quantum gates working on qubits. A gate either might be a unary gate working on a single qubit, or it might a 2-qubit gate, so a gate which works on more than 1 qubit. Sometimes, or frequently, we also may have gates which work on more than 1 qubit. And of course, just for the sake of completeness, a qubit is literally the equivalent of a conventional bit. So we're talking about quantum qubits in the quantum realm, and for short, qubits. So usually a quantum circuit may look like that. So we have literally a set of qubits, which is shown here. We've got a set of operations. And in this particular example, this is a C0 operation, a controlled NOT operation, which simply works on qubit 0 and qubit 1. And we have similar descriptions which look like that. This is a kind of assembly-like programming language, which now in a sort of textual way describes all the single gates we have here on the left-hand side in terms of an ASCII text. So this H gate here, for example, working on Q2 is basically defined here, and this controlled NOT operation or controlled X operation working on Q0 and Q1 is defined here. And by this, we can describe quantum circuits and systems on algorithm. And now the typical design flow, the typical compilation flow is that you usually start with your algorithm described, for example, in terms of a quantum circuit, or maybe in terms of higher programming languages, which are available for quantum computing. And as you can see, we might have here even gates which are composed of which work on more than 2 qubits. In this case, we have a gate which works on 3 qubit. So this is usually your first conceptual algorithm. And now you want to realize this algorithm in terms of this quantum circuit on a particular target device. And the target device is usually the constraints imposed or needed to be satisfied on a target device are usually described in terms of a graph as shown here. And this graph now basically describes what kind of qubits are allowed to interact with each other. So in this example, qubits Q0 and Q1 are allowed to interact with each other because they are connected with an edge, while, for example, qubit 0 and qubit 4 are not allowed to directly interact with each other. So those are the constraints you have to satisfy on the target device. And this is one of the motivation why we now have to sort of compile or map or transpile. There exist several terms for it. Our task is now how to sort of compile, translate, transpile, map this overall circuit into a structure which can be executed on this target device. And for this purpose, we have, as said, we have to satisfy these constraints here, but we also have to satisfy that a target device can only realize a limited gate set. It means the first task is we have to check whether all our operations of our given circuit are composed of operations which can be executed on a target device. And in this example here, let's simply assume that this gate here cannot be executed on a target device. So the first thing we have to do is we have to replace or we have to decompose or compile this gate into a sequence of elementary gates which are supported by the corresponding device as shown here. So this part of the circuit now is composed of elementary gates only, and they realize the same functionality as this gate. So this is actually the circuit we can execute on the device. And now we have another problem that we have to, as I mentioned before, we have to satisfy that only, in this case, Q0 and Q1 and Q1 and Q2 and so on can interact with each other. And this causes a problem, particularly at this position here. That means if you, for example, say that, okay, now our qubits, our logical qubits from the circuit, Q1 and Q2 and Q0, are mapped to the physical qubits Q2, Q1, and Q0 in exactly this relation, then we can execute all those gates on this architecture because, for example, here, this gate can nicely be executed because this qubit here is now mapped to physical qubit Q2. This qubit is mapped to physical qubit Q1. Q1 and Q2 have an edge, so this gate can be executed. However, this gate here, which would follow after this one, could not be executed because this gate argues over logical qubit Q0 and Q1, which have been mapped to physical qubit Q0 and Q2. And you can see Q0 and Q2 are not connected. So accordingly, this gate cannot be executed on this device. So what we have to do is we have to move the corresponding qubits together. This can be done by the swap gates here. These swap gates simply swap, as the name suggests, the positions of this qubit. With this, I now swap Q0 to Q1. So now my logical Q0 is on the physical Q1 next to the physical Q0. And now I can execute the C0 gate here again. And by this, my entire circuit. So this is the mapping process. And then if I have that, then finally, in order to address limited fidelity and covariances, I have to optimize my circuit. And this can be done, for example, by removing redundant gates, as shown here. 2 H gates in a row simply cancel each other out. They can be removed, but also gate combinations like that can be removed. And then I eventually end up with a resulting circuit, which I really want to execute on my architecture. So this is sort of the flow, the compilation flow. And now what the hell has this to do with such solvers? Well, many of those steps I just described here are actually actually NP-hard problems, so problems, typical EDA problems, which have been proven NP-hard. And by this, of course, are very interesting to get tackled using SAT solvers. And I will explain that now in the following, because particularly this task getting from this description here to that description there is a typical NP-hard problem. And here, SAT solvers can actually help solving this problem. So this is the first use case of SAT solvers in quantum computing I want to illustrate. So again, what is the main idea? The main idea is you want to satisfy these CNOT constraints. You want to make sure that qubits only interact that gates only interact on qubits which are actually satisfied, which actually allowed to interact with each other. So again, maybe let me illustrate that on this example here. So let's consider this circuit here composed of a series of CNOT gates. And now let's assume that all those qubits here are mapped as shown here. So logical qubit 0 is mapped to physical qubit 14. Logical qubit 1 is mapped to physical qubit 15. And this graph here literally describes what kind of interactions are allowed and what are not allowed. So as an example, this interaction here between logical Q2 and logical Q3 are allowed because they are mapped to logical Q0 and logical Q1 respectively. They are next to each other. They are allowed to have interaction, so we can execute this gate here. In a similar fashion, these two qubits here work on two neighboring physical qubits as well. So this is also allowed as well. However, here we have a problem because this qubit here is mapped to physical qubit 3. This is mapped to physical qubit 0, and Q0 and Q0 are not allowed to interact with each other. So this gate cannot be executed yet. So as you can see, the same for this gate here, and so on and so forth. As you can see, there are a couple of so-called CNOT constraints which are not satisfied, namely exactly for these three gates marked with this red cross here. Now, usually it is not possible to find a mapping from all the logical qubits to all the physical qubits, which allow to satisfy all the constraints for an entire circuit. Usually having one single mapping, one single order of qubits usually does not guarantee that for all of the other gates. So what you usually do is you change the mapping of logical qubits to physical qubits in between. And that's what I mentioned before, can be done with swap gates. That means with a gate which looks like that, which simply takes two qubits and then basically swaps their position. So if we originally map logical qubit Q0 to physical qubit Q0 and logical qubit Q1 to physical qubit Q1, and then apply the swap gate here, we simply swapped or permuted the positions of the corresponding logical qubit. This can be realized with a sequence of gates, quantum gates like that. And usually this is also translated in, or can be translated into a sequence such as this here. Not always, depends on the architecture, but long story short, these kind of swap gates can be used in order to satisfy these CNOT constraints. And now, getting our example back, what we can do right now is we can, well, take our original circuit, derive an initial mapping, and then we check, okay, whenever is in current gate satisfying the CNOT constraints. This was, as we showed before, the case in this first gate here. It was the case in the second gate here. So we can simply leave these gates unchanged. But as you might remember, this gate here did not satisfy those CNOT constraints. We have those two qubits are not allowed to interact. But we can now solve that by adding a swap gate, which moves logical Q4 and Q5. And then by adding another swap gate like this, then we literally, I go 2 steps back, you can really see how we sort of move this qubit closer to the other qubit, which it needs to be interacting to. And by doing that, I eventually can realize this single gate here. Of course, I changed the order of qubit assignments by that, but eventually this allows me to execute this gate here. And then I can now do the same for this gate here, which again works on qubits which are not yet close to each other. By adding further swap gates, I can move them together so that they can be executed. And this I can now literally do for all the remaining gates. Here we already have nothing to do, but for this gate here, we have to move these two qubits together again with one single swap. And this is my overall circuit. And as you can see, this is a classical combinatorial problem, right? So this is something, of course, this now leads to a solution, but the real problem right now is this really the best possible solution? Is this the solution which yields the smallest amount of swap gates, for example? And this indeed has been proven as an NP complete, NP hard problem. And for this is a great problem where subsolvers can be utilized. And in fact, there has been approaches which use such solvers in order to tackle this problem. And in the general idea, of course, is to solve that problem in the minimal fashion, in the best possible fashion. What you have to do is you have to consider all possible permutations before each gate. That means if you have a circuit, let me move that here. If you have a circuit like that and you want to derive the best possible mapping of the circuit to an architecture, that means the mapping with the least amount of swap gates, then what you could do is you can simply consider before every gate all possible permutation. This is described by this picture here. At the very beginning, of course, you can arbitrarily apply an arbitrary order. Then you execute the first gate, which is the C0. The unary gates like the H gate here and the T gate, they can be ignored because they only work on a single qubit. There's no C0 constraints to be satisfied. They're already satisfied by the definition. So the first gate is this C0 gate working on logical qubit 3 and 4. So 3 and 4 before this gate, you basically can employ an arbitrary permutation. And later on, after this gate, you may not necessarily have to, but you may have to change the order of your qubit mapping so that you then also can satisfy the C0 constraint for this gate here. So literally what we're saying is, in order to get the best possible solution, the solution with the minimum number of swap gates, you have to consider all possible permutations before all possible gates. And in a naive fashion, of course, you can do that by enumeration. And then for each permutation, you check out who's satisfying the C0 constraints, calculate the number of swap gates required for that in order to realize all those permutations, and then simply choose the one with the smallest cost. This yields to a tremendous complexity. Namely, we have before each gate, we have to check out n factorial permutations. And obviously this scales not very well. So obviously if you do this in a numerative approach, you have a rather huge complexity. But this is exactly the kind of problems subsolvers are very suited for. So what we can do instead is we can try to solve the same problem using a satisfiability-based solution. And for this, all we have to do is we have to formulate that problem in terms of a satisfiability problem. That means in a symbolic formulation, which covers all possible solutions. Then, which describes all possible solutions, then we need to invoke a set of constraints so that out of all possible solutions, we only get, or the subsolver only determines the ones which are valid, which solves our problem, and at the same time remain minimal. And then all we have to do is we have to pass that to a subsolver. The subsolver gives us this assignment or proves that no such assignment exists. And out of this assignment, out of this result, we then can derive the resulting mapping. So how can we do that? Well, first again, describe all possible solutions in a symbolic fashion. What does it mean? Well, that means that we have to that means we have to encode what is our actual problem. And we can do that by using these four X variables here. That means for this particular line, this is a physical qubit we are mapping logical qubits to. And we now simply say, okay, for each line and each variable represents whether or not at position number 1, so this is this index here, this first index at position number 1, this position means before gate number 1, this variable, it's a Boolean variable, which describes whether or not logical qubit 1 is mapped to a physical qubit 1 or not. While this variable here now represents whether or not logical qubit 2 is mapped to physical qubit 1. And this variable describes whether or not logical qubit 3 is mapped to physical qubit 1. And this obviously states whether or not logical qubit 4 is mapped to physical qubit 1. So with these variables, I symbolically describe all possible logical qubits which may be mapped to physical qubit 1. And then I'm doing that, of course, for the second physical qubit as well. So this literally states that at position 1, that means before gate number 1, this states whether or not logical qubit 1 is mapped to physical qubit 2, and so on and so forth. And then, for example, these variables here, they state whether or not before position 2, so before the second gate, whether or not logical qubit 1 is mapped to physical qubit 4, and so on and so forth. So I hope you get a little bit the idea that with all those variables, I symbolically describe all possible mappings of logical qubits to physical qubits, right? And this is literally the entire search space of my problem, because this encapsulates and formulates all possible logical to physical qubit mappings. And out of all those possibilities, now I, of course, want to have this mapping, which satisfies which is valid and which satisfies my my CNOT constraints, and which are at the same time minimal as well. Well, and in order to do this, I now have to restrict possible solutions. That means I have now to employ constraints. And the first set of constraints is sketched a little bit by this formula, because of course, the first thing you have to make sure is that for all those variables, you only want to have exactly one variable set to 1, right? Why is that? Because again, if let's assume all those x variables would be set to 1, then we would literally state that on position 1, logical qubit 1 is mapped to physical qubit 1. And then if this is 1 as well, we would state that logical qubit 2 is mapped to physical qubit 1 as well. And logical qubits 3 and logical qubit 4 would be mapped to physical qubits 1 as well. So obviously we don't want that. We want just have one logical qubit to be mapped to physical qubit 1. And that's the reason why we have a constraint. This is actually this constraint here, that we want to make sure that at least either no logical qubit is mapped to here, or at most one logical qubit, right? And this constraint is simply the other way around, the constraint of the other way around, that we make sure that, of course, every logical qubit has to be mapped to at least one physical qubit. So with this constraints, we ensure that, of course, the mapping of logical qubits to physical qubits is consistent. This satisfies our first constraint, right? However, this literally now describes an arbitrary mapping of each logical to each physical. But of course, we also now want to have constraints which satisfy our CNOT constraints or our coupling map constraints. That means we want to have constraints which make sure that Q3 and Q4 actually are allowed to interact with each other. And for the first gate, and for the second gate, that Q1 and Q2 can interact with each other. So what we're doing is we're checking for all those gates, we're checking the two qubits, which are denoted by QC and QT here. And then we're checking what kind of constraints are allowed to have interaction with. And then we simply check out, okay, if there's, for example, allowed to interact between physical qubit I and physical qubit J, we make sure that the corresponding QC, logical qubit C and logical qubit T are accordingly assigned here. And I hope the rough idea comes through. Of course, the terminology is something you have to get used to. Long story short is simply that now if we enforce these constraints, we make sure that, of course, still arbitrary assignments can be made as long as they are valid, as long as they are consistent, and as long as they actually allow that these two logical qubits get a physical qubit mapping which allow them to interact with each other. So this is literally ensuring that interaction is possible. So, and if we have that, then we actually now really can force a subsolver, for example, to assign all those variables so that only valid logical to physical qubit mappings are assigned, and assignments which satisfy the CNOT constraints. And now we have to additionally enforce that, of course, an assignment and mapping is derived, which is minimal. And to this end, we have to understand what kind of permutations, which need to be realized by swap gates, are employed. That means if we have a particular assignment here and a particular assignment there, we have to describe and we have to formulate what permutation these realize and how many swap gates I would need to realize that. The first one can easily be done by adding another variable here, which simply states that, okay, here the second permutation is this variable y here is assigned to 1 if at the second position, that means before gate 2, a permutation pi is realized, which maps the respective assignment from this, from here to the respective assignments from those variables. So this is literally what is described here. We basically have variables checking the corresponding x assignment and the corresponding y assignment, checking what kind of permutation is employed from here to there, and then setting the corresponding y variable to 1. That means out of all possible permutations, we are setting exactly one variable to 1, namely the one which realizes the permutation according to the current assignment of those x variables. And then knowing what permutation is employed, we now employ a cost function, namely this one here, which simply states, okay, we know we can pre-calculate how many swap gates we need in order to realize a permutation pi. Then we know that a single swap gate has cost of 7. That means we calculate 7 times the number of swap gates we needed to realize pi. And then if at the current position, y pi is 1. That means if this permutation indeed is realized by those x assignments, then we enforce that those costs are added to our overall costs. And by this, we literally describe our cost function, namely that we now got an objective function. And now we've got an instance, an satisfiability instance composed of all those x variables, of all those y variables, with all those constraints. And now the subsolver is enforced to find an assignment to all those x variables so that the assignment is valid, so that this assignment satisfies the coupling constraints, the C0 constraints, and that the resulting permutation yields to costs which are minimal. And this literally solves our mapping problem in an exact fashion, because all we have to do right now is we have to take this formulation, path it through a subsolver, and then the subsolver is supposed to generate an assignment, and an assignment which minimizes this cost function. And out of this assignment, we can determine the corresponding logical to physical qubit mappings. And by this, we can determine the resulting minimal mapping. So this is literally what we can be done, and it solves this problem by using subsolvers. And as said, this is a solution which has been already implemented and investigated quite heavily. And with this, I just want to show you what kind of potential this solution has. In fact, with this solution, so this columns here literally describe how many gates are needed in order to map certain quantum circuits to a particular architecture. And without the mapping process, we ended up with those costs. After the mapping process, that means after adding swap gates, we ended up with those costs. Those costs now have been proven to be minimal. And here we additionally listed, here we additionally listed the number of gates, the cost which would be required using, for example, IBM's Qiskit. And then you can really see the difference that in many, many cases, for example, here we have costs which are 44 times, which are by the value 44 higher than with the minimal approach. So this nicely shows the potential subsolvers have. With the subsolvers, we are able to determine the minimal costs for those mapping problems. And you can see those minimal costs are sometimes substantially smaller than the costs using other tools. I hope this wasn't too much at once, but I hope you got a little bit the idea. It's a typical combinatorial problem. It can be solved in an exact fashion using subsolvers. Of course, scalability will remain an issue. You can see the runtimes here. You can see that we applied it to rather small circuits only, but there are also some ideas of how to improve the performance. So that, for example, you could consider a subset of physical qubits only. You can restrict possible permutations. All this will, of course, not guarantee minimality anymore. So the results won't be exact anymore, but evaluations showed that there's close to minimal. So, and the main idea is that all that is something where subsolvers can really nicely be used. And for more details, I'm referring to a corresponding paper which has been made available on this URL here. And I also would like to quickly encourage you, if you want to play around with that, all that what I just have described is also publicly available as an open source implementation. We even have integrated that into Qiskit. So what you can actually do is you can simply write in Python script as basically shown here on the left-hand side. I'm just showing that directly. So this is a quick Python script which incorporates Qiskit and which incorporates our own tool chain, which you can simply download or clone from this GitHub repository. And then by simply typing down those commands here, you basically can solve an corresponding mapping problem in rather short runtime using subservers using reasoning engines. All right, so I know lots of stuff to digest, but I hope you got an idea. It is very similar to the conventional realm where we have combinatorial problems and use subservers, constraint programming, reasoning engines in general in order to solve the corresponding solution. So this is, in my opinion, the example I wanted to show you as an example of a use case which offers huge potential. Now to the second part of my talk, and I promise this is not going to be as long as the first part, because here I'm actually not presenting a completely solved problem, but merely some sort of ideas what can be used, because with this direction, we also have a couple of obstacles, of challenges to overcome. And this is a little bit also related to the entire flow, because a typical question you might have in quantum computing, in this quantum computing design flow, is of course question which you also find in the conventional world. For example, is eventually the functionality of this circuit here at the top with which we started, is this equivalent to the circuit we ended up with here as an actual realization? And of course, this is an equivalence checking problem. And you might know that, of course, in subsolving, equivalence checking problems have frequently been used or solved using subsolvers by formulating a MITRE structure and translating that into a corresponding SAT instance and then get the solver solving that. But we also have similar problems for test pattern generation and for model checking, property checking. So we have lots in the conventional realm, we have lots of solutions where subsolvers are utilized. And the main idea in all those solutions is that you simply take a circuit and then you encode the circuit in terms of a satisfiability instance, which literally means you assign each signal with a particular variable, and then you represent each signal with a variable, and then you enforce constraints like that, which actually realize the corresponding functionality, but now in terms of an SAT instance of a SAT logic. And then what you simply do is you pass encodings like that, you add corresponding constraints, for example, a MITRE structure, in order to make sure that if you have two circuits, the inputs are assigned the same and the outputs check whether or not they now realize different output values. And then what you simply do is you take the circuit encoding, you formulate your design task, and then you pass it to a SAT solver. And then the SAT solver determines the SAT solver determines a corresponding assignment. And out of this assignment, you can then conclude the solution or derive the solution to your design problem. So basically, each assignment to the X variable represents a valid circuit assignment, and further constraints are added, for example, to encode a verification or test problem. So this is something which is very established in the conventional realm. And now the question is, can we do that for quantum circuits as well? And the answer is a little bit, well, technically yes, but for real practical problems, it's going to be a challenge. So let me illustrate that a little bit. In quantum circuits, we merely have the same situation as in conventional circuits. We've got signals, if you allow this term in this context, and we have operations. So what we can do is here, we can have a signal. And of course, right now, the signals could be zeros or ones. So we have maybe something like that. Both signals are assigned to 0. And this in general is very similar to the conventional world, although in the typical quantum state descriptions, we describe that in terms of these vectors here. Then, however, we have the problem that we not only rely on values zeros and ones, but also on, as you probably know, anything in between. In quantum circuits, we have superposition. And this means that if I apply a gate like that, I, on the one hand side, get this following signal here, which simply remains the 1. But since this is 1, this Z gate is now executed. And this Z gate now changes the state from 1 to -1. so yielding another slightly different circuit. If I measure this, this qubit here, if I would measure this qubit, I still would get one, but it's in a different phase, which needs to be represented. And if I do further, if I apply this state now to an H gate, I now get this typical, very well-known superposition state. And if I apply this state here to this H gate, and again get a superposition state, which however now is slightly different to the superposition state from before. So long story short is, technically, I can use exactly the same idea that I represent values of a signal with variables and then apply operations. The only difference here is that I have to, I don't only have values 0s and 1 as in the conventional realm, but I actually got, in the worst case, an arbitrary amount of states. So this could be seen as a problem at the first glance, but one way to solve that is actually to check out beforehand how many states would you need, because many quantum circuits actually assume sort of a restricted set of input states at the beginning. For example, this quantum circuit here might be there might be an understanding that those states can only be 0 or 1. So we have a restricted, a limited set of possible states. And what you could do is you could now do an analysis as shown here in this table, that you say, okay, I've got these two quantum states which I need to represent. And now I'm checking and analyzing what sets of further state might result out of that. That means if I apply these states on an H operation, I have to check out, okay, this is the state 0 here and the state 1. If I apply an H operation, I may end up in this state and in this state. And because of that, I know that maybe, okay, those are two further states I need to support. And this qubit state here might be in either one of those states. And then in a similar fashion, I know, okay, the same happens here. So here I get the same set. No new possible values are going to introduce. So because of this analysis, I know that up to here, my circuit might be in one of those 4 states. And I may have to think about, okay, how to translate states from here with the H operation. And that's literally what I have to do so far, because other operations are not going to be executed here. Now, if I consider this X gate, I now can conclude, okay, this X gate might be employed to states described by this one here. That means this X gate here now has to be considered for this state and for this state. So I can calculate, I can make the corresponding calculations. And by this, I can derive, okay, now I may need another state, namely this one here, which is this one. This state here has already been considered. So this map now shows, this table here now shows all the potential states I need to represent, namely all those 5 states, which this circuit may assume, and all possible state transitions, which need to be encoded. And with this, I get a description, a combinatorial descriptions of all possible states, all possible operations. And now technically using this table, I now could derive an multi-valued sub-encoding, which describes all those possible states and transitions. And this is a finite set of quantum states and a finite set of operations to be encoded, something what can be done in order to realize a set instance. And we did some preliminary studies, and indeed by using an analysis like that and multi-valued encoding afterwards, we are indeed able to do an SAT-based equivalence checking, for example. So here we have a couple of instances. We check the equivalence of corresponding instances. This may require a substantial amount of variables, but as you can see, the number of states to be encoded are finite, so they are limited. So this is something which can work out, but the problem, the obstacles, of course, is that the number of states, they grow. They can be kept small, but they grow significantly. And for those cases, the time remains efficient. But the real problem is right now, what happens if you come up with a really huge quantum circuit, which may impose a huge number of quantum states? Then you have a problem. And something which I completely ignored so far, A huge problem is also going to be what happens if you not only working with control, with these kind of control lines, something, but the issue, the main obstacle is what happens if you have to deal with entanglement. This is something what happens if you cannot represent, give me a second, this is something which you cannot represent in this fashion anymore, but when you have to represent quantum states, not in a fashion as a single state vector here anymore, but what happens if you have to represent a quantum state which argues over 2 qubits at the same time? This frequently occurs, particularly when it comes to entanglement. This is a particular example. A circuit like that, or a state at this position here, cannot be represented separately for each qubit anymore, but both qubits together have to be constitute one state which have to be represented, and this is becoming a huge challenge. So, however, I'm running out of time, and I hope at the end of the day, the things I mentioned in the last slide, I hope you got a rough idea. Otherwise, I'm happy to continue these kind of discussions with you in the Q&A. What is the main take-home messages of this talk? Well, first, as said, many problems, for example, compilation problems, as I showed here, they constitute classical standard combinatorial problems where subsolvers can help. This is what I wanted to convey in the beginning of my talk. Beyond that, however, there are lots of other potential of subsolvers, which we, for example, know from the conventional realm, and which we can in a similar fashion also try to utilize in the quantum realm. But here we have obstacles, like how to find in sub-encoding which handles entanglement in a very efficient fashion. This, in my opinion, are obstacles where we have some ideas, but something which we cannot completely, where we don't have a completely satisfying solution here right now. But this is something where I would love to start a discussion with all of you. And if you have any ideas, if you're interested in that, I'm really happy to do this afterwards, after this presentation here. As a final remark, please excuse this brief, this shameless plug here, but as a final remark, of course, all of the implementations I've shown here and all of the ideas I've shown are available. More information is available on our webpage, but we also have many of software solutions, some of them using subsolvers, some of them, as you can see, also using others like decision diagrams. Many of those solutions are available as open source implementations and might be interesting for you as well. And also, if you don't want to deal with GitHubs and don't want to install any tool, we also have a web-based tool which you can play around a little bit on certain tasks. And this is the final shameless plug I wanted to do here in order to also show you some of the tools and software which is already available. And with this, I would like to thank you again for your time, for your interest. And as said, if you are interested in this kind of direction, feel free to approach me, ask me any questions, drop me an email, leave me a message. Those are questions in the past. I've worked a lot with subsolvers and subsolvers in the classical design automation. And now I'm really keen of utilizing this potential for the quantum realm as well. Thanks again and take care.